Hi, today we are going to discuss Chapter 7 of Ionic Equilibrium. Now, let's discuss a basic buffer solution. A basic buffer solution is prepared by mixing a weak base and its conjugate acid. For example, a mixture of a weak base of ammonia and the salt of ammonium chloride. The reaction that occurs in the basic buffer solution as shown in the equation. There are two types of reaction that occur in the solutions. First, the dissociation of the weak base and the dissociation of the salt. The weak base in the solution are partially dissociated in the aqueous solution, while the salt are completely dissociated in the aqueous solution. In these basic buffer solutions, the ammonia acts as a dominant base. The presence of the hydroxide ion is very small amount due to the partially dissociation of ammonia. The ammonium ion acts as a dominant acid in this buffer solution, that is, mainly from the complete dissociation of the ammonium chloride. When a small amount of strong acid is added to the solution, most of the H+ ion added will be consumed by the ammonia to form ammonium ion. The chemical reaction as shown in the equation, whereas ammonia is react with the H+ added to form ammonium ion. The equilibrium position for this reaction will shift to the right, thus the concentration of the ammonia will decrease and the concentration of ammonium ion will increase. As a result, there will be only a small change in pH. Besides, the hydroxide ion from the dissociation of the base will also react with the added H+. The chemical reaction as shown in the equation, whereas the hydroxide ion react with H+ added to form water. The equilibrium position will shift to the right to increase the amount of the H+ that is consumed in the reaction. Thus, the NH4+ ion will increase in concentration and the ammonia will decrease in the concentration. As a result, there will be only a small change in pH. But when a small amount of strong base is added to the solution, the hydroxide ion added will be consumed by the ammonium ion of the conjugate acid to form water. The chemical reaction occurs as shown in the equation, whereas the ammonium ion react with hydroxide ion added to form ammonia and water. The equilibrium position for this reaction will shift to the left, thus the concentration of ammonia will increase and the concentration of ammonium ion will decrease. As a result, there will be only a small change in pH. Now, let's discuss on how to calculate the pH for a basic buffer solution. Let's consider the same example of a basic buffer solution that contains of ammonia and the ammonium chloride. The dissociation constant for this buffer solution can be expressed as Kb equals to concentration of the ammonium ion times concentration of the hydroxide ion divided by concentration of the weak base of ammonia. Kb expression can be rearranged in terms of concentration of the hydroxide ions. By placing the negative log on both sides of the equation, it will obtain an equation of POH equals to pKb plus log concentration of the ammonium ion divided by concentration of the ammonia. In general, the equation shows the expression of POH equals to pKb plus log concentration of the salt or the conjugate acid divided by concentration of the weak base. The above equation is called Henderson-Hasselbalch equation. Now, let's discuss an example on how to calculate the pH of a buffer solution. First question is, calculate the pH of the buffer solution that contains 600 ml of 0.10 molar of ammonia and 400 ml of 1.50 molar of ammonium chloride. The Kb value for ammonia is given 1.8 exponent -5. Since a buffer solution is a mixture of weak base and the salt. Therefore, we need to determine the final concentration of ammonia and ammonium chloride in the buffer solutions. We can use M1V1 equals to M2V2 equations. By substituting the value, it will obtain the final concentration of ammonia and ammonium chloride with 0.06 molar of ammonia and 0.60 molar of ammonium. From the concentration obtained, thus we can determine the pH of the buffer solution. By using the Henderson-Hasselbalch equation for a basic solution, the substitution value will obtain pOH that equals to 5.74. To determine the pH of these solutions, we can use a formula of pH equals to 14 minus pOH. Thus, it will obtain the pH value with 8.26. Now, let's calculate the pH when a small amount of a strong acid is added to the basic buffer solution. When 0.011 molar of hydrochloric acid is added, the H+ ion will completely consumed by the base in buffer solution. The reaction occur can be written in the ICF table. The ammonia aqueous solution will react with the H+ ion that is added from the strong acid to form ammonium ion. Since only a small amount of acid is added to the solution, thus H+ will be the limiting reactant. At the end of the reaction, they still have a remaining ammonia with 0.049 molar and ammonium with 0.611 molar. By using the Henderson-Hasselbalch equation, substituting the value of the concentration obtained from the ICF table, we'll obtain the pOH value with 5.84. To determine the pH, we can use the formula of pH equals to 14 minus pOH. Thus, it will obtain the pH value with 8.16. Now, let's calculate the pH when a small amount of strong base is added to the buffer solution. If 0.15 molar of NaOH is added, the OH- added from the strong base will completely consumed by the conjugate acid in the buffer solution. The reaction occur can be written in the ICF table. The ammonium ion react with OH- to form ammonia and water. Since the strong base added is only a small amount, therefore the OH- will be the limiting reactant. Finally, the ammonium chloride remain after the reaction is 0.45 molar and ammonia with 0.21 molar. By substituting the value into the Henderson-Hasselbalch equation for the basic solution, therefore it will obtain the pOH value with 5.08. To determine the pH, we can use the formula of pH equals to 14 minus pOH. Thus, it will obtain the pH value with 8.92. So, we can make a conclusion that is, an acidic buffer solution, we can determine directly the pH from the formula of Henderson-Hasselbalch that is pH equals to pKa plus log concentration of a conjugate base over concentration of the weak acid. For a basic buffer solution, we can determine the pOH by using the Henderson-Hasselbalch with a formula of pOH equals to pKb plus log concentration of the conjugate acid divided by concentration of the weak base. Now, let's try these questions. Which of the following are buffer systems? Click the pause button if you need more time to answer the questions. Now, let's check the answer. For A, HF is a weak acid and the fluoride ion is the conjugate base. Thus, this is a mixture of a weak acid and its salt, so it is a buffer solution. B, HBr is a strong acid. Thus, this is not a buffer solution. For C, the NaHCO3 is a weak base and the CO3 is a conjugate acid. Thus, this is a mixture of a buffer solution. You can try to answer this exercise questions. So, this is the end of our lessons today. We'll see you next time. Bye.